Okay, so for, gosh, over 2,000 years, we've basically lived with this idea, right?
Mm-hmm.
That our universe is, three spatial dimensions: length, width, depth, plus time.
The familiar four dimensions.
Hmm.
4D space-time.
Exactly. And we thought that's enough. Enough to map everything from, I don't know, this microphone to the furthest star.
It's a powerful model, held since the ancient Greeks, really. But, well, it seems that that view is, let's say, starting to crumble under the weight of modern physics.
Crumble how?
Well, theoretical physicists, they're increasingly thinking the universe has to exist in a higher dimensional space. We often call it hyperspace.
Hyperspace. Okay, that sounds a bit sci-fi.
It does, but it's actually probably the most rigorous path forward we have right now to try and unify everything, to get that one elegant theory of reality.
Right. And our sources for this deep dive, they get into the weeds on this. Names like Kaluza-Klein theory, supergravity.
And the big one today, superstring theory. That's the main contender.
And superstring theory, it doesn't just say more dimensions, does it?
Yeah.
It gets specific.
Very specific. That's the amazing part. The mathematics. For it to work, for it to be consistent, it demands a precise number.
Which is?
10. 10 dimensions in total. 1 of time, 3 of space we see, and 6 more. Hidden ones.
6 hidden dimensions. Wow. Okay, so our mission today is to figure out why. Why 10? What's the math saying?
Ah.
And what does it all mean for, well, everything?
Exactly. What does it mean for physics, for reality, maybe even for getting around the universe?
Okay, let's unpack this idea of unification first.
Yeah.
So the main driver behind looking for these extra dimensions, it's this idea called the principle of elegance, right?
That's a good way to put it, yeah. The
Yeah.
fundamental laws of nature. They should be simple, elegant, whole. Not the kind of messy, patched-together picture we have now.
Right, because right now things seem complicated.
They do, and the sources use a great analogy. Imagine you're stuck here on Earth's surface,
Okay.
and you're trying to figure out seasons. Why summer? Why winter? Why do winds blow certain ways? It all seems incredibly complex, just local rules.
Yeah, it feels random almost.
But then you launch yourself into space. You get a higher perspective, a third dimension, vertically.
And suddenly,
Suddenly it's obvious. You see the Earth tilted on its axis, that 23-degree slant orbiting the sun, and all those complex weather laws, the seasons, they just click into place as simple geometry.
I see. From a higher dimension, the complex becomes simple.
Precisely. And physicists think that's what's needed for their biggest headache, unifying the 4 fundamental forces.
Okay, remind us. Gravity.
Electromagnetism, and then the 2 nuclear forces, strong and weak.
Right. And the problem is they don't play nice together in our current 4D model.
Not really. Gravity is described beautifully by Einstein's general relativity, which is classical. But the other 3 forces, they live in the quantum world. Totally different rule books. Trying to get one equation for all 4 in just 3 spatial dimensions seems, well, impossible. The theories are just too small.
But we have seen unification happen before, haven't we?
We have. Einstein himself did the first major one. He took James Clerk Maxwell's work on electricity and magnetism.
Which was like 8 different equations. Kind of clunky.
Very clunky. And they treated space and time as totally separate. Einstein realized that by adding time as a 4th dimension, making space-time, he could collapse all that complexity into one beautiful relativistic equation for electromagnetism.
Wow, so adding a dimension simplified everything.
Massively. That equation now governs everything from light to radios to GPS. It was the proof of concept. Add a dimension, gain elegance and unity.
And that leads us to Kaluza, Theodore Kaluza.
Exactly. He took the next logical step back in the 1920s. He thought, well, if adding the 4th dimension, time, unified space-time, and electromagnetism relative to space, what if we add a 5th dimension, a spatial one this time?
Okay, what happened?
Something incredible. He took Einstein's equations for gravity, which already worked in 4D space-time, and just reformulated them for 5D.
Yeah.
And out popped Einstein's original gravity equations, naturally. But also, a second set of equations fell out.
Don't tell me.
Maxwell's equations. For electromagnetism. Perfectly.
Whoa. So just by adding the geometry of a 5th dimension, electromagnetism just appears as part of gravity.
That's what the math showed. It suggested electromagnetism isn't some separate force. It's just gravity doing its thing, but spilling over, vibrating in that unseen 5th dimension.
Mind-bending. He unified 2 forces using only geometry.
Kaluza's insight was profound. It suggested matter, forces.
Yeah.
They aren't fundamental things in themselves. They're just ripples and curves in the underlying geometry of space-time. The wood of matter is just an illusion created by the marble of geometry.
So if we want to unify all four forces,
We just need to keep adding dimensions. We need enough geometric room for all the forces to emerge as different aspects of the same overall shape.
which eventually led to superstring theory needing.
10 dimensions.
Here's where it gets really interesting.
Okay.
Kaluza needed 1 extra, 5 total. Why does superstring theory jump all the way to 10? That seems like a lot. Why not 6 or 8 or 12?
It's purely down to mathematical consistency. It sounds arbitrary, but it's not. When physicists tried building string theories in, say, 4 or 6 or even 26 dimensions initially,
Yeah.
the math broke down. You'd get impossible answers like probabilities greater than 1 or negative probabilities, or these things called quantum anomalies, inconsistencies that basically make the theory predict nonsense.
So the theory eats itself unless...
Unless it's formulated in precisely 10 dimensions. 1 time, 9 space. Only in 10 dimensions do all the nasty infinities perfectly cancel out. All the quantum anomalies vanish. It's the only number of dimensions that allows for a mathematically sound, consistent framework where both quantum mechanics and gravity can coexist peacefully.
So the universe has to be 10-dimensional for the math to even work.
According to superstring theory, yes. The elegance and consistency only appear in 10D. The laws of physics simply don't make sense otherwise.
The universe is mathematically destined to be this big, complex structure, even if we only perceive a fraction of it.
That's the idea. We're like fish unaware of the air above the water.
Which, okay, brings us right to the big problem for us.
Yeah.
How on earth do we visualize that? We're 3D beings.
It's incredibly difficult, maybe impossible, directly. Hermann von Helmholtz had that great line explaining a fourth spatial dimension to us is like trying to explain red to someone born blind. Our brains just aren't wired for it.
So we rely on analogies.
Primarily, yes. And the best one, the classic one, is Flatland. Edwin Abbott's little book from 1884.
Ah, yes, Mr. Square.
Mr. A Square.
Right.
A proper gentleman living in a world of only length and width, no concept of up or down.
Right. He can move side to side, forward and back, but that's it.
And then a 3D being, Lord Sphere, decides to visit Flatland. How does he appear to Mr. Square?
Well, the sphere passes through the 2D plane.
Yeah.
So Mr. Square only sees the slice, the cross-section.
Exactly. He sees a circle appear out of nowhere, then it gets bigger, then smaller, then vanishes.
Terrifying for the Flatlanders.
Yeah.
Unexplainable.
Utterly. It's this constantly changing, bizarre shape. But it's the proof. Proof that their 2D world is just a slice of a higher 3D reality. Proof their world is curved in a way they can't directly see.
So by analogy, if a 4D hypersphere passed through our 3D space,
We wouldn't see the whole object, we'd just see a 3D cross-section. Maybe a sphere appearing, growing, shrinking, changing shape in ways that seem to violate our known physics, then vanishing. It would be deeply unsettling.
it's wild that this purely mathematical idea, the fourth dimension, actually spilled out into popular culture back then, wasn't it?
Oh, massively. It caused quite a stir in the late 19th century. You had that bizarre case with the psychic Henry Slade around 1877.
The guy who did weird tricks, like
Right.
linking 2 solid wooden rings together.
That's the one. And respectable scientists like Johann Zollner actually tried to explain it rationally using the fourth dimension.
How would that even work, linking rings?
Well, think about knots. A knot in a rope only stays knotted in 3 dimensions, right? In a hypothetical 4D space, you could just lift one part of the rope into the 4th dimension, pass it over or through the other part without intersecting in 3D, and then drop it back down. The knot is gone without cutting the rope.
Whoa.
Same idea with the rings. You could lift one ring into the 4th dimension, pass it through the solid barrier of the other ring, and put it back. They'd be linked. Zollner thought Slade might be unconsciously accessing this higher dimension.
Crazy.
Right?
But it shows how the idea captured imaginations. And it wasn't just psychics, right? It hit art, too.
Absolutely. Think about Cubism, Picasso and Braque. They were trying to break free from that single-point perspective Renaissance art had locked in for centuries.
Where you just see the object from one angle at one moment.
Exactly. Cubism tried to show an object from multiple viewpoints all at once. Like you're seeing the front, the side, the top, all overlaid.
Which is kind of how a 4D being might perceive a 3D object, seeing all sides simultaneously.
That was part of the conceptual leap, yes. Rejecting the limitations of our 3D perception, it was a revolution in thought, spurred by mathematics.
Okay, so we have this visualization problem, but let's get back to the physics. If superstring theory needs 10 dimensions for the math to work, where are the other 6? I mean, I can see 3. Length, width, depth. Where are the rest? Why aren't we bumping into them?
Right. This is probably the most critical piece of the puzzle. And the answer lies in an idea called dimensional compactification.
Compactification. Sounds like squishing.
That's basically it. The theory proposes that right after the Big Bang, the universe started out as this perfect 10-dimensional space-time, highly symmetrical, very elegant,
But unstable.
inherently unstable. Almost instantly, that perfect symmetry shattered. 4 dimensions, the 3 space, and one time we know exploded outwards. That's the expansion of the universe we still see.
Okay. And the other 6?
They did the opposite. They collapsed, curled up on themselves into incredibly tiny, tiny shapes, probably loops or complex structures called Calabi-Yau manifolds,
How tiny?
like Planck-Lengthany, around 10 to the minus 33 centimeters. Absolutely minuscule, far too small to ever perceive directly or even probe with our most powerful particle accelerators.
So they're curled up
Yeah,
like looking at a garden hose from far away.
that's a great analogy. From a distance, the hose looks like a one-dimensional line, right?
Yeah.
But get up close, and you see it has a second dimension, the circular cross-section curled up around a length.
Ah, okay. So we live in the long part of the hose, the 4 big dimensions, and we just don't notice the tiny curled up ones.
Precisely. But even though they're tiny, their shape, their geometry is crucial.
How so?
Because the specific way those 6 dimensions are curled up, that geometry dictates the properties of the fundamental particles and forces we do see. The vibrations of strings in those tiny dimensions give rise to electrons, quarks, photons, and mediate the strong and weak nuclear forces.
So that's where the other forces come from. They're reflections of the geometry of the hidden dimensions, completing Kaluza's idea.
Exactly. The entire standard model of particle physics, in theory, emerges from the geometry of those compactified dimensions. It's all geometry, just in 10 dimensions instead of Kaluza's 5.
Okay, so the structure is dictated by this hyperspace geometry. Now, for the really wild stuff, if this geometry is the fabric of everything, could we maybe use it? Like, could it allow us to take shortcuts, tunnel through space and time, wormholes?
Ah, yes. Wormholes. This is where the geometry of general relativity gets really interesting. Mathematically, wormholes are possible solutions to Einstein's equations. They represent tunnels or bridges,
Connecting distant parts of space? Or maybe even time?
or even potentially parallel universes. They're sometimes called multiply connected spaces. Think Alice falling down the rabbit hole or through the looking glass. That's the concept.
And these aren't just pure fantasy. There's math behind them.
Oh, yes. Solutions like the Schwarzschild black hole initially seemed to have a mathematical feature, the Einstein-Rosen bridge that looked like a tunnel, though it turned out you couldn't actually cross it. Then the Kerr solution for rotating black holes looked more promising, perhaps connecting to a mirror universe.
But could you actually travel through one? That seems like the key question.
That became a serious focus thanks, oddly enough, to Carl Sagan. When he was writing his novel Contact, he wanted a scientifically plausible way for his hero to travel interstellar distances quickly.
So he asked a physicist.
He asked Kip Thorne, a leading expert on general relativity at Caltech. Thorne and his colleagues took the challenge seriously, and they found something surprising.
What was that?
They found mathematically simple solutions that described traversable wormholes, tunnels that wouldn't instantly collapse, wouldn't crush you with infinite gravity, tunnels you could theoretically pass through.
Okay, traversable wormholes. That sounds like a game changer.
Yeah.
So space travel between stars or even galaxies becomes possible.
Mathematically possible, yes. But Thorne's solutions came with a very big catch, a huge engineering challenge.
There's always a catch. What is it?
To keep one of these tunnels stable, to prop its throat open long enough for something to pass through, you need something weird. You need what physicists call exotic matter.
Exotic matter.
Specifically, matter that has a negative energy density or negative pressure, something that gravitationally repels rather than attracts.
Negative energy. That sounds like it breaks the laws of physics.
Yeah.
Like anti-gravity stuff from bad sci-fi.
It sounds impossible, I know. It's incredibly counterintuitive. Positive energy density is what all normal matter and energy has. But it might not be completely impossible.
Really? Oh.
Thorne and his team pointed out that quantum mechanics might actually allow for pockets of negative energy density, specifically through something called the Casimir effect.
Casimir effect. Okay, what is that?
All right, imagine you take 2 perfectly smooth, uncharged metal plates, and you put them incredibly close together in a perfect vacuum, like microns apart.
Okay, empty space between them.
Not quite empty. According to quantum field theory, even a vacuum is fizzing with virtual particles constantly popping into and out of
The
existence.
quantum foam.
Exactly. Now, between the plates, only virtual particles with certain wavelengths can fit. Outside the plates, all wavelengths can exist. This difference creates a tiny pressure imbalance,
Meaning.
meaning there's slightly more pressure pushing on the outside of the plates than on the inside, so the plates are pushed together by the vacuum itself.
Wow. And that's been measured.
Oh, yes. First predicted in 1948, measured reliably by 1958, and refined many times since. It's a real physical force caused by quantum fluctuations. And that region between the plates, the one with lower pressure,
That is negative energy density.
effectively, yes, it demonstrates that negative pressure or negative energy density relative to the surrounding vacuum is physically possible according to quantum mechanics. It's real.
So the exotic matter needed to stabilize a wormhole. It might actually exist, thanks to quantum effects.
It suggests it's not forbidden by physics. Now, harnessing enough of it to stabilize a macroscopic wormhole across light years, that's an unbelievable engineering challenge, maybe impossible. But the possibility seems allowed by the laws of physics as we understand them.
So if we could somehow create and control enough negative energy, tunnels through space-time using the geometry of hyperspace could be real. Time travel, interstellar shortcuts.
The math allows for it, provided you can solve the negative energy problem. It connects back to the fundamental geometry.
So what does this all mean? Where does this journey leave us?
Well, it's a huge shift in how we think about reality, isn't it?
Yeah.
We went from Einstein's 4 dimensions, which was already a leap, to superstrings 10. And it reinforces that vision Kaluza had a century ago.
That geometry is fundamental.
Exactly, that the marble of space-time geometry is the true bedrock. And matter, forces, the wood that makes up our universe, they're just patterns, vibrations, expressions of that geometry. Unification through shape.
And the key takeaway seems to be, don't trust your common sense when it comes to the universe.
Pretty much. Our intuition is built on 3 spatial dimensions. But the math, the drive for elegance and consistency, points beyond that. Adding dimensions doesn't complicate things. Paradoxically, it simplifies the underlying laws. It allows gravity and the quantum world to finally merge into one framework.
Science isn't just about what we see, but what the math predicts is necessary for consistency.
Precisely.
Okay, so let's leave our listeners with a final thought to chew on, based on all this.
Right. Consider how we sometimes measure civilizational progress. There's the Kardashev scale, based on energy mastery.
Type I controls a planet's energy. Type 2 controls its star.
And a hypothetical Type 3 civilization could harness the energy of an entire galaxy. Now, if manipulating or even detecting the 10th dimension, tapping into that full hyperspace geometry might require something on the scale of Type 3 energy.
Energy levels thousands, maybe millions of years beyond us.
What kind of almost unimaginable leap in science and technology would we need to make just to even begin to experimentally confirm that our familiar 4D reality is just, well, a shadow, a fragment of a much larger 10-dimensional whole? What does that gap tell us about our current place in the cosmos?